In this lesson, we will discuss symmetric and skew symmetric matrices. Before going to start the questions of symmetric and skew symmetric, I will introduce you a few terms which we already have discussed in lesson number 1 and 2 in detail. But again, I am going to explain to you because you have to use these terms when we will solve the questions of skew matrices or symmetric matrices. Okay, first is the transpose of a matrix. So transpose of a matrix is obtained by interchanging rows into column. Now what does it mean? Suppose we have one matrix, any elements you can write down here, right? So horizontally it is called rows, vertically these are columns. A transpose means how we will represent A transpose, or sometimes people also say A dash, so both are same. A transpose, rows by interchanging rows into columns. So see, this is the row 2 3, this is the row, make it column. Second is 4 and 6 is the row, make it column. So this is the A transpose. Another example, suppose if we have B, any number, you can write down any elements, right? Now, B transpose, if someone asks you what will be the B transpose of B, so very simple. This is first row, make it column 1 4 0 8 7 6. This is the row converted into column. This is called the transpose. So transpose of a matrix obtained by interchanging rows into column. This term we will use in the next few slides. Now the square matrix. Square matrix means number of rows is equal to number of columns. Suppose we have A matrix and we have these entries. So what is the order? This is called row. There are 2 rows. How many rows? There are 2 columns and 2 rows. So number of rows is equal to number of columns is called the square matrix. One more example, suppose we have, so here we will make 3 by 3. 1, 2, 3, 3 rows and 3 columns. So if someone asks you what is the order, what is the dimensions of matrix B, it means number of rows and number of columns. Always keep in mind, first you have to mention rows, then column. So this is the square matrix. Number of rows is equal to number of columns. If suppose we have like this, so here number of rows are 2, number of column is 1. This is not the square matrix. Right? So transpose of a matrix, just convert rows into column. Square matrix, number of rows is equal to number of columns. Now we will use another term here. It is called the symmetric matrix. Now what is the meaning of symmetric matrix? There are 2 conditions, right? If a matrix is available and if someone asks you whether it is a symmetric matrix or not, then you have to see that whether that matrix satisfies these 2 conditions or not. The first condition is the matrix should be a square matrix. See, that is why I have explained a square matrix in the last slide, because it is used in the symmetric. Very important. First is, suppose again we have this matrix A, right? So question is whether it is a symmetric matrix or not. So what you have to do, first you have to check that it is a square matrix, number of rows is equal to number of columns. Yes. So first condition is satisfied. What is the second condition? A transpose, and we have discussed transpose. What is the A transpose? A transpose of this will be, make this 6 and 8 as a column, 7 and 2 as a column. When we will take the A transpose, it should be the same as A, and A is this 6, 8, 7, 2. This is not the same, so this is not the symmetric matrix. Symmetric matrix has to satisfy both conditions. So see, suppose here I am writing another matrix, suppose A. You can have any name, B, C, X, Y, D, the name of the matrix, right? But this is just the journal. I can say here, right, B transpose, if the name of the matrix is B, so I will say B transpose should be equal to B in order to be a symmetric matrix. So here suppose this is A, and here I will write down suppose 2, minus 3, 4, and minus 3, 5, 1, 4, 1, and minus 3. If someone asks you whether the matrix A is a symmetric matrix or not, so first of all you have to see whether this matrix satisfies the first condition, 1, 2, 3, 1, 2, 3. Dimension is 3 by 3. Number of rows is equal to number of columns. It is a square matrix, so you can go further. The first condition is satisfied. Now A transpose. A transpose is, this is the first row, make it column 2, negative 3, 4, negative 3, 5, 1, 4, 1, negative 3. And check A transpose. What is the second condition? A transpose should be equal to the original A matrix. So this one is the original. So see, both are same. If we take the transpose of this matrix, it is same. So this is the symmetric matrix. So we say AT is equal to A, right? Both are same. So this is the symmetric matrix. Right? Another example I will give you. Suppose now this is B. Instead of A, I am writing B. So you should know that any letter we can use. 3, 4, and this is 4 and 1. First condition is A is a square matrix. So here we can say B is a square matrix because the name is B. 2 rows and 2 columns. Yes, first condition is satisfied. Go to the second one, B transpose. Now we will take the B transpose. Means we will convert this as first row, make it column. This is second row, make it column. And now C, B transpose is equal to B. This is the journal formula, right? So whatever is the name of your matrix, you have to use that one. So B transpose, this is the transpose, should be equal to B. It is B, 3, 4, 4, 1. Both are same. So this is the symmetric matrix. So for the symmetric matrix, the matrix should satisfy two conditions. First is it should be a square matrix. When we take the transpose of this matrix, it should be equal to the original matrix. Right? Now, this is the important thing. Skew symmetric matrix. For a skew symmetric matrix, again the same thing. It should satisfy, the matrix should satisfy the two conditions. First, it should be a square matrix. Same thing, number of rows is equal to number of columns. But the second is, if we take the transpose of the matrix, it should be equal to the negative of A. Whatever is the A matrix, it should be equal to the negative of A. Here I will show you the example, okay? Then it will be make more clear. A is equal to, here I am using the same letter for matrix, but in the next few examples I will change it. So you should know that you can have any letter, 0 and this minus 1, 0, 1. This is suppose 1, minus 1, 0. This is the matrix. And if someone asks you whether it is a symmetric matrix, sorry, skew symmetric matrix or not, first is you have to find out whether it is a square matrix or no. 1, 2, 3, 1, 2, 3. Its dimensions are 3 by 3, means number of rows is equal to number of columns. So first condition is satisfied. Now is the second. Second is take the A transpose I told you convert rows into columns. So minus 1, 0, 1, 1, minus 1, 0. 0, 1, minus 1, and then minus 1, 0. Okay, so this is the A transpose. Right? In the case of symmetric matrix, you have to see that whether this A transpose is equal to this original one. But for the skew symmetric matrix, you have to see that this A transpose should be equal to the inverse of this original one. So what is the inverse? How you will write down inverse? A inverse of A, just change the sign. If it is positive, make it negative, and if it is negative, make it positive. So we will get, here you have to change both. So this is the negative of A, and this is the transpose. So see, this transpose and this minus A both are same. It means this is the skew matrix. Skew matrix. Right, first condition is you have to see whether it is a square matrix. If it is not a square matrix, you should not go ahead. But if it is a square matrix, then you have to go to the second condition, and second condition is A transpose. So two things here you have to do. First you have to make the A transpose, then you have whatever the A matrix is, make it, change the sign of each element, which is called the inverse, and then you have to see whether these two are equal or not. If these are same, it means it is a skew matrix. Now another example. Suppose B. Here I am going to tell you very important thing. Like this. This is a skew symmetric or not? First is you have to check the number of rows and number of columns. So see, it is 2 by 2. First condition is satisfied. Move on to the second one. Take B transpose. B transpose is 6, 4, 3 and 2. Right? 6, 4, 3 and 2. And now take, this is B transpose, now negative of B. So what is the negative of B? Negative of B is minus 6, minus 4, minus 3, minus 2. See, B transpose is not equal to this one, minus B. Both are different. So this is not the skew matrix. So we can say here, this is very important point. These are called the diagonal elements. These are the diagonal elements. If the diagonal elements are non-zero, these are not zero, it can never be a skew matrix. For a skew matrix, diagonal elements should be a 0. So this is the important thing. If the, see here, this is the diagonal elements. That is why I have made this question. These are the diagonal elements and it is the skew matrix. But the diagonal elements, if, keep in mind, if the diagonal elements are not 0, we can never have a skew matrix. But if we have the diagonal matrix, it is not compulsory that always it will be a skew matrix. Maybe it will be a new skew matrix or maybe not. Here, maybe or maybe not. But if it is non-zero, it can never be a skew symmetric matrix. We have proved it here. Okay, now I will give you the example of a C matrix here. See, it is 0, 2, minus 2 and 0. See, now here is this diagonal matrix. This is diagonal entries are 0. But when we will take here, now we have to see whether it is a skew matrix or not. So this is the original one. Take the transpose of this. It will be 0, 2, minus 2 and 0. Right? And what is the second condition? C transpose. Now instead of this A, we have C transpose should be equal to minus C. So negative of C will be 0, minus 2. This one, I am going to make, this is the original C. Minus 2, sorry, this will be 2. This is not minus. and this is 0. So C transpose, this one, equal to negative of C. If we take the negative of this, so this is called the skew symmetric. I told you that if it is a 0, if the diagonal elements are 0, the matrix may be skew matrix or maybe not. But if it is not 0, it can never be a, close your eyes and say it is not a skew matrix. Right? Okay, here one more example. Now D. See, for D I say 0, 1 and 4 and 0. Now we have to prove whether it is a skew symmetric or not. Number of rows and number of columns are equal. Take the transpose, D transpose. See here, now I am taking D instead of this A. So you should know any letter we can use. Transpose 0, 1, 4, 0. And this transpose should equal to the negative of this original one. So what is the negative of this? It will be 0, minus 1, minus 4 and 0. See, both D transpose is not equal to the inverse of D. This is negative 1, this is 4, this is this one. Right? So what we proved, what we conclude that for the skew symmetric matrix, first of all you have to see that whether the matrix satisfies the first condition, number of rows is equal to number of columns. Then take the transpose of the matrix, it should be equal to the negative of the original matrix. What is the name, right? If the diagonal matrices are non-zero, it can never be a skew matrix. But if the diagonal elements are 0, like in this case, and in this case, it may be a skew matrix or may not be. See, in these two, these are skew, but here diagonal is 0, but it is not the skew matrix. Now we will solve some questions, then you will understand more. So this is A is equal to this matrix, B is equal to this, then verify that A plus B whole transpose is equal to A transpose and B transpose. So we have to prove this. This is the left hand side, this is the right hand side. First we will solve the left hand side, which is A plus B, right? A plus B whole transpose. So first of all we will, okay, I will write down like this. A plus B whole transpose is equal to, what is A? A is 1, 2, 0, 1, and B is 1, 1, 2, 0. And when first we have to add and then we will take the transpose. So see, I will do in one step. 1 plus 1 corresponding entries you have to add. How you will add? 2 plus 1, 0 plus 2 and 1 plus 0. Right? This is whole transpose, which is equal to 2, 3, 2 and 1. And now we will take the transpose of this. So which will be equal to, I am writing here. Make the rows into columns. This one. This is the left hand side, or we can say A. Now we have to prove AT plus B transpose. So what is the A transpose? First I will write down A transpose here. A transpose is 1, 2, 0, 1. This one. And B transpose equal to 1, 1, 2, 0. So question is A transpose plus B transpose, which is equal to 1, 0, 2, 1 plus 1, 2, 1, 0. Add it. It will be 1 plus 1, 0 plus 2, 2 plus 1, and then 1 plus 0. Corresponding entries you have to add together. So A transpose plus B transpose is equal to 2, 2, 3 and 1. So this is the right hand side B, and you will see A and B both are same, 2 2 3 1, 2 2 3 1. So we have proved that A plus B whole transpose is equal to A transpose plus B transpose. Right, next question is, if A is equal to this, B is equal to this, then we have to verify A negative B whole transpose. Same question, but only the sign is different. So A minus B transpose. Right, first we will solve left hand side, which is equal to A 1 2 0 1, negative of 1 1 2 0, and then see whole transpose. This is in the parenthesis and this is whole transpose. At the end we will take the transpose. So 1 minus 1 corresponding entries you have to subtract. Same thing for subtraction and addition. But if you have any question, without hesitation you can ask me. I will try my best to solve it. This one, and then take the transpose. So 0 1 minus 2 1. This is the A or left hand side, you can say. Now we have to move on to the right hand side. A transpose. First we have to find out A transpose, make rows into columns. B transpose 1 1 2 0, and then A transpose minus B transpose equal to 1 2 0 1. Subtraction of 1 2 1 0. Just subtract it. 1 minus 1 corresponding entries. And now you should know what is the meaning of corresponding entries. The first element of the first matrix with the first one, second with the second one. Similarly, first and second. These are called the corresponding entries, and then it is negative 2 and 1. So this is the right hand side. Now you have to see that A and B, 0, negative 2, 1, 1, 0, negative 2, 1, 1, both are same. So we have proved that A negative B whole transpose equal to A transpose minus B transpose. It is proved. Now this is the important, and if I am writing here important, it means you have to practice this 4 or 5 times. Very important question. It may come in your exam. Symmetric. If A is equal to this matrix, B is equal to this, then you have to verify A plus A transpose is symmetric. See, so far we were using letter A for a matrix, letter B, letter C, right? Whatever. But for this matrix, in order to prove this theorem, suppose your matrix name is this, A plus A transpose, right? You have to prove that A plus, you are not going to find out A plus A transpose. No, you have to find out whether A plus A transpose is symmetric. And I told you for symmetric there should be 2 conditions. These matrices should be square matrix, first condition, and when we will take the transpose of this, it should be equal to A. Right, started. A is this, and then A transpose is this, A transpose. So we will write down here like this. A plus A transpose, A is 1 0 2 1. This is A. Now, what is the A transpose? 1 2 0 1, and we will add it. When we will add 1 plus 1, 2 plus 2, see, you have to do step by step because step also counts. Number 2 2 2 2. Now see, this is the important point here. Now we have add 2 matrices, A plus A transpose, and now we have only one matrix here. This is called A plus A transpose. Instead of letter A, B, X, Y, Z, suppose we have the name of a matrix this. Forget about the rest of the part. Suppose our question starts from here and this is the name of our matrix. So from here we will start the question, and here we will see whether this matrix satisfies these two conditions. It is a square matrix. Yes, it is a square matrix. A transpose is equal to A. See this one, this is the name of our matrix. Instead of only one letter A, B, so far we were doing, this is the name of complete name of our matrix. So what is the second condition? A transpose. So it means this is the name of our matrix. So A plus AT, suppose this is B, right? You have to take the transpose. This is the important point. The important point starts from here. Suppose this is the name of our matrix. Instead of a single letter A or B, we have this. So you have to take the transpose of this, because the second condition is A transpose. Whatever is the name of your matrix, take the transpose, and then see when we will take the transpose, it is 2, 2, 2, 2, and it should be equal to A. So now our A is this one. Forget about this thing. So see, A plus A transpose is equal to our original one, this one. Both are same. It means that A plus A transpose is symmetric, and this is the theorem. This is the theorem, and very important theorem. Right? Same thing we will do with the B as well. Same thing, right? Instead of A, now we have B. B plus B transpose is symmetric. We have to prove this. The question is whether it is symmetric or not. The question is not that you have to find out B plus BT. No, you have to prove. So for symmetric, first is it should be the square matrix, and here B transpose should be equal to B. Okay, now first we will add, and here in this case our matrix name is B plus B transpose. Just like this is A, this is B, right? We just take that B transpose. In this case, our matrix name is, suppose B plus B transpose is equal to 1, 0, 2, 1, and then B transpose. Sorry, this is, I have to change it. You should be very careful in math. See, I have written by mistake matrix. This is B 1, 1, 2, 0, and it is 1, 1, 2, 0. Add it, corresponding entries you have to add 1 plus 1, 1 plus 2, 2 plus 1, and 0 plus 0. So which is equal to 2, 3, 3, and 0. So what is this? This is B plus B transpose. Question is not this one that you have to add B plus. No. You have to prove that whether it is symmetric or not, and again this is important. Important means you have to practice it. So suppose this is the name. This is the name of our matrix. Instead of a single letter, we have B plus B transpose. So the question will start from here. This is our matrix. Forget about the rest of the part. What is the square? Whether it is a square matrix? Yes, it is a square matrix. Now B transpose. So this is complete is B. It means you have to, this is the name of our matrix. You have to take the transpose of this, and which will be 2, 3, 3, 0. See, this is our B. This is our original B, and this is the transpose. Both are same, 2, 3, 3, 0. It means B plus B transpose is symmetric. It satisfies both conditions. It is a square matrix. It is a square matrix as well as B transpose. So from here the important point starts. Right? Okay. Now for this one we have to check whether A minus AT. The question is not that you have to subtract only A minus A transpose. The question is, this is the theorem, whether it is a skew symmetric matrix or not. So what is the condition for this skew symmetric? First is it should be a square matrix. Second is when we take the transpose of the matrix, it should be equal to the negative of A. But this is journal A, B, C. Whatever is the name of the matrix we will use. So here first is A minus A transpose. A minus A transpose equal to, first we will subtract it, 1, 2, 0, 1. And what is the transpose? Transpose is 1, 2, 0 and 1. 1, 2, 0, 1. This is A, and 1, 2, 0, 1. Right? So subtract it. Same thing, corresponding entries, 1 minus 1, 2 minus 0, 0 minus 2, 1 minus 0. So it will be 0, 2, negative 2 and 1. No, this one, 0 minus 2 and 1 minus, this is, see, I told you, you should be very careful, otherwise 1, 1 minus 1. So see, if something happens, if you will do error in your mathematics, do not find out your error. It is time consuming. Just do the question again. Right? A minus A transpose. So this is A minus A transpose. A minus A transpose 0, 2, negative 2 and 0. Now the question starts from here. This is the important point. First of suppose, forget about these things, right? A minus A transpose, we did it. So suppose now this is our matrix and the name of our matrix is A minus A transpose. So first of all, you have to see whether it is a square matrix. Number of rows is equal to number of columns. First condition is okay. Second is take the transpose. Now see, this is the name of our matrix. So we will take the transpose of this, which will be equal to 0, 2, negative 2 and 0. Right? This one is the transpose. Transpose should equal to the negative A. So this is our A. Do not change the sign of this A. Now this is our question. This one is the A. So what is the inverse of A? Here I will show you, negative of A minus A transpose equal to 0, negative 2, positive 2 and 0. So see, negative, this is the transpose and this is the negative. Both are same. It means A minus A transpose is skew symmetric. So we have proved it. Right? Last question. B minus B transpose is a skew symmetric. Again, we have to prove. The question is not that you have to subtract B minus B transpose. No, you have to prove whether it's a skew symmetric or not. First of all, we will see whether it is a square matrix or B transpose should be negative of B. This is also very important. You have to practice. So B minus B transpose equal to, what is B? 1, 1, 2, 0 from here. Right? And then you have to subtract the transpose, make rows into columns. So corresponding entries, 1, 1 minus 2, 2 minus 1, 0 minus 0. It will be equal to 0, 1, negative 1 and this is 0. So this is B minus B transpose, right? This is B minus B transpose, but this is not the question. Question is, you have to prove whether it is a skew matrix or not. So our question will start from here. This is the important, star means important point. This is the star, right? So suppose this is our B matrix, this one. Instead of B, we have B minus B transpose. Question starts from here. So see, what is the first is square matrix? Yes, it is a square matrix. Then take the transpose of B. So this is, instead of one letter, we have this. So make the transpose of this. Transpose of this equal to 0, -1, 1 and 0. Right? So it should be equal to the negative of B. So what is B? Now this is our B. Do not consider this one. It's done. Now this is our B. So negative of B is equal to, just change the sign. It is this, -1 and 0. So see, B minus B transpose. This is B is 0, 1, -1, and this is also 0, 1, -1 and 0. Both are same. It means B minus B transpose is skew symmetric. And again, I am saying that this is a very important concept. You have to practice 2 or 3 times. The question, you have to consider this one as a B. So see, this is B transpose. Instead of one letter of the matrix, the name is this. So you have to take the transpose of this, and then you have to change the sign of this matrix in order to see whether these two are equal or not. But still, if you have any question, without any hesitation, you can write down in the comment section. But do not forget to subscribe to my channel, Saima Academy, and thanks for watching.